Good day, everyone. Today, we will present our paper entitled Underwater Image Enhancement using Fusion-Based Deep Neural Net. I am Jinzhang Liu from National Zhongzheng University, Taiwan. This is the outline of our presentation. First, we will give a brief introduction. Then we will present the proposed approach. Then we will show some experimental results, followed by concluding remark. As we know, underwater images are usually degrade images due to insufficient light color distortion and water flow tracking. Underwater image enhancement approach can be split into 4 categories: enhancement-based, restoration-based, fusion-based, and learning-based. Enhancement-based approach usually convert the original underwater image into some transformed domain and then perform image enhancement. For restoration-based enhancement approach, image formation model was used to enhance underwater image by estimating transmission map and background light. For fusion-based enhancement approaches, some image fusion techniques are used to enhance underwater image by fusion 2 or more pre-processing images. For learning-based enhancement approach, different deep neural nets are employed to enhance underwater image. In this study, an underwater image enhancement approach using fusion-based deep neural net is proposed. As shown in Figure 1, given an input underwater image, 5 pre-processing techniques are used to generate 5 pre-processing underwater images. Then 5 feature transformation units are separately used to compute 5 future map of the 5 pre-processing underwater images respectively. Based on the input and the 5 pre-processing underwater images, 5 confidence map for the 5 pre-processing underwater images are estimated. Finally, the 5 future map and the 5 confidence map are together used to generate the enhanced underwater image. In this study, 5 image pre-processing techniques, namely image blurriness and light absorption removal, gamma correction, constant contrast, limited adaptive histogram equalization, relative global histogram straightening, and the removal of water straightening are employed. This is the framework of the proposed approach. Gamma correction is a power law transformation defined as equation 1. There are 7 fusion-based neural nets in different image and vision application. Water net is modified and employed in this study, as shown in Figure 2, to extract features from the 5 pre-processing image. 5 feature transformation units (FTU) are separately employed to generate 5 corresponding feature map. Figure 2 shows the feature transformation unit. To extract feature in many image and vision tasks, convolution and pooling with image downsampling and the receptive field enlargement are employed. Then image upsampling is used to expand image resolution. However, pooling and downsampling usually induce image information loss. So in this study, direct convolution, which expand receptive fill and maintain image resolution is employed. In this study, to perform image downsampling and image upsampling, max pooling and bilinear interpolation are employed separately. In this study, for activation function, namely sigma, TANH, ReLU, and switch are employed. Sigma is defined as equation 2. TANH is defined as equation 3. ReLU an activation function for reducing the problem exploiting gradient and managed gradient is defined as equation 4. Switch, a smooth and non-monotonic function for improving the ability of gradient expression is defined as equation 5. To maintain stable input distribution in each layer, in this study, batch normalization BN is employed. As shown in Figure 3, UNet and encoder-decoder architecture with skip connection can perform end-to-end training with small number of training samples. So, pixel attention module, PA module, is used to make deep neural net pay more attention to important features, which is defined as equation 6. As shown in Figure 4, using element-wise modification of IPA and IN is performed. Note that UNet and modified PA module are employed in the proposed feature transformation unit, FTU. Figure 3 shows the architecture of UNet. Figure 4 shows the architecture of modified pixel attention PA module. As shown in Figure 5, the proposed confidence map estimation module is employed to perform confidence map estimation. As shown in Figure 6, based on the previous attained map and features, the final enhancement underwater image IEN is generated as equation 8. This shows the proposed confidence map estimation module. Figure 6 shows the image future architecture. In deep neural net, mean square error, mean absolute error, and Hopper loss are usually employed as loss function. In this study, Hopper loss is employed and defined as equation 9. In this study, adaptive motion estimation ADAM optimizer is employed, which will be described in equation 10, 11, 12, 13, and 14. This slide shows the system setup of the proposed approach, and we use two data sets, UFO and UIEV. We will have 5 comparison approach and 4 objective metrics, including PSNR, SSIM, UIQM, and UCIQE. In terms of average PSNR, SSIM, UIQM, and UCIQE performance comparison between 5 comparison approaches and the proposed approach on UFO dataset are listed in Table 1. Similarly, performance comparison between fab comparison approach and the proposed approach on UIEB dataset are listed in Table 2. Similarly, performance comparison between fab comparison approach and the proposed approach on UIEB challenging 16 are listed in Table 3. Figure 7 shows some experimental results on UFO dataset. Figure 8 shows some experimental results on UIEB dataset. Figure 9 shows some experimental results on real-world image. Concluding remark. In this study, an underwater image enhancement approach using fusion-based deep neural net is proposed. Based on the experimental result obtained in this study, in terms of objective metric and subjective evaluation, the performance of the proposed approach is better than those of fab comparison approach. Thank you for your attention. Thank you.